Welcome to the live session on FPGA based signal processing systems. So in this live session, we would like to address first few questions if you have on assignments or any of the lectures, and then Ma'am Shanti would take over to explain about the FIR and IR filter design using the MATLAB. How do you generate the coefficients and the other responses, and how MathWorks can be helpful in this filter design, FTA tool, and so on. Okay. So the questions can assignment to this filters. Are you facing any problems to solve the assignment questions? So a few questions on, see, one is on fixed point and floating point representation. Actually, these options were given for floating point representation, and we have dropped that question, but still you can have answer the question related to the that question related to floating point, but we have dropped that question. So again the doubts are coming up with the need of clarification. That is one thing. And the setup time and hold time, that question is correct. Before and prior, these are the words which have been changed in the setup time and hold time definition. So there is no problem in that question. That question is correct, and answers are, you can answer that. Only in this part, the fixed point needs to be floating point single precision, then the options are valid. So anyway, the question itself is having the typo, so we have just dropped this question. So we need not answer the question. That will not be taken into account for grading. So any of you need clarification in any other questions? There is this assignment is based on this week 8 assignment is based on just some of the Verilog modules have been given. The representation, and then this is based on timing analysis actually. Okay, so we have explained this problem also, how to solve it in the last live session, how to compute all the other parameters related to this circuit, digital circuit which is given. Okay, so especially the timing parameters. Okay. And the week 9 assignment is this is based on the filters actually. See FIR and IR filter design. This is basically the MCQ and MSQ types, that in which you would have basic what is the FIR filter definition and IR filter definition, and the output of each of them. The impulse responses are decided by which inputs and the outputs. So the IR would have the feedback, and the present and past input samples as well as the past output samples are used to decide the current sample. Similarly, in case of FIR, that is a little different. The case is it doesn't take the past output into account to decide the present input. So the structures have been asked. FIR filter direct form 1 and 2. What is the structure and what is the order of the structure? And these are the tabs, and we have given the codes, Verilog codes, also in one of the lectures related to it. And the co-filter, which is the response h of z, you need to obtain, and from that h of z, what is the phase and what is the amplitude of it. And because it's a co-filter, that you would have the you have to see the magnitude and the phase response in it and answer the question here. there are 8 zeros on the unit circle. Okay, it's given the comb filter itself, and what should be where the location of the poles and zeros would be, how many poles and how many zeros, and what are the, and in the FAR filter, which is there are 4 categories: type 1, 2 and 3 and 4. So in type 1, 3 midpoint symmetric or midpoint anti-symmetric. This is just testing that coefficient. So because FAR filters has the linear phase characteristics, we would have the coefficients are midpoint symmetric or midpoint anti-symmetric. So which type of filter it is? Okay, so that's the question here, and yeah, well, based on the type 1, 2, 3, 4, and if you find the frequency response and the impulse response for the type 1 linear phase filter, which one would be it would obey? Yeah, please, you have a question, please. Anybody has a
Yeah.
question? Yeah.
Yes, ma'am. Good morning, ma'am.
Good morning. Yeah.
Ma'am, can you please explain the question number 18 of assignment number 9?
This one, 18.
Question number 18, ma'am.
Yeah, let us open.
Yes, ma'am.
Yeah, the low pass filter rectangular window in which 9 samples and a cutoff frequency 2 radians. Which
Yes,
of the
ma'am.
filter coefficients are correct for the design? Okay, so similar
Okay.
problem we have solved in one lecture. In the lecture, you can see that how the rectangular window is used, and
Yes,
the
ma'am.
cutoff frequency is only the difference we have here. It is so 2 radians per second, and even you can calculate this using the equation given in the lecture.
Yes, ma'am.
Uh,
Sure.
and substitute that n varying from 0 to 8. Here 9 samples are there. Okay.
1, 2, 3, 6, 7, 8. Yes, ma'am. 9. Total 9.
And in the h of n expression, obtain the h of n expression for the filter given this equation. That is sinc function you would get.
Okay.
The equation also is given in the lecture. You can, if you follow this example in the lecture, similar example is given. Only the cutoff frequency is different here. Take the expression of h of n, that is obtained actual filter design. Desired is something when you multiply with the window, you would get the impulse response. That is nothing but the coefficients h of n. That h of n in the expression of sinc. You substitute n equal to n 0 to 8 and you would get the coefficients. What are those coefficients? That's what we are asking. And you can use the MATLAB FDA tool as well for this design to get the coefficient.
Okay, ma'am. Thank you, ma'am.
Yeah. So similarly, in this case, the ripples in the design of FAR 19 using the windows with the cutoff frequency 2 radians, the stop band ripples for different window types are what are they? See, there are stop band attenuation for different windows. Refer to the table which is given. Okay, the stop band ripple reduces as we move on from rectangular window to smoothening windows, right? So you would get a better and better side lobe response in these windows, rectangular, Hanning and Hamming Blackman. So find out this, what is the stop band ripple, which is given, suppose it is 13.3 dB for rectangular window. 20 log of del S equal to 13.3 minus 13.3, equate it and get this ripple value. Okay, that's the rectangular. And similarly for Hanning, it is specific. It is given in the table around 26 dB. Hamming also, and Blackman. Those dB side lobe level, first side lobe level needs to be taken for computing the ripple. Here in 19.
Understand, ma'am. Thank you. Thank you so much.
Yeah. And next one is done. 10. Yeah. In the assignment 10, so it's related to IIR filters, in which I have explained the two analog filter designs using two. One is that Chebyshev and the Butterworth. So design it for Butterworth and Chebyshev filter design, and then discretize this using the impulse invariance method or the bilinear transformation. Two methods only we discussed in the lecture, and the questions are related to this. Which of the following can be used for digital IR filters, that's the discretization process. Also, the structure of the digital IIR filter is given. So, IIR has the feedback coefficients as well, not only feed forward coefficients. So, in that case, which of the following is correct related to the IIR filter? Okay, so equations, you match with the equation and the structure and answer it accordingly. Also, this is two types of IIR filters, and the third structure is related to the reduction in redundant delays of the structure. So instead of having the two types of delays in the previous structures, 3 and 4, at least in 4, and the fifth one is the more modified or the optimized structure here. So you're reducing the number of delays in the structure. The sixth question is about impulse invariance method. If you refer to the mapping between the analog and digital domain, or the analog S plane and the Z plane mapping, it talks about the question is about the mapping. It's one-to-one mapping, or every strip in the impulse invariant method is mapped into the units inside the unit circle. So it is more stable also. But because it is not one-to-one mapping, it's a many-to-one mapping, because you will have the strips, different strips in the S plane. So these strips, every strip will get inside the unit circle in the Z plane. So it's not one-to-one mapping, it's a many-to-one mapping. And in the bilinear transform, we have the question is about the bilinear transform. Again, it is used to discretize these analog filters into the discrete ones. What are the mapping? This question about the mapping, it is one-to-one mapping here. Okay, so it's not the many-to-one. And this question, Butterworth filter and use impulse invariance method. I think the similar example is given in the lecture. Please follow the lecture for question 8. You have to find the coefficients. What are the coefficients you get? One feed forward coefficient and one feedback coefficient. And what is the sampling time you obtain for the given specification? Okay. That's about 8. And the 9 is getting, for the same question, get the similar one, get the equation of it in the time domain equation. What is the time domain equation? Which one is correct for the time domain equation? And then the question 10, he has given, this is given a pole pattern. Okay, so pole pattern, Butterworth filter, what is the pole pattern? It is a circle, right? In the S plane, it will occupy the circular fashion, left half of the S plane and the right half of the S plane. So the radius of that circle is the cutoff frequency. So that's what the question is about. Given the pattern.
Second answer is correct, na? Question number 10.
No, you need to calculate it actually. So how many is the correct? How many poles are there, and is it forming the circular pattern? And what is omega c? All of them needs to be calculated. Yeah. Okay, so that is one, and then 11 is type 1 Chebyshev filter. What are the again? There are two types of Chebyshev. One is only discussed in the lecture, because second one is not discussed. We have not done it. Type 1 will have this monotonous response in the stop band and the ripple combination needs to be, it will be exchanged in the type 1 and type 2. So what related to the elliptical pattern, the pole location, if you see, that would be an elliptical pattern in the S plane. So that's this question is about which is it elliptical pattern or the circle pattern of circle. So type 1 will have the ripple in the pass band and monotonic response in the stop band. So what are the ripples? What is the order? Order can also be identified from the ripple fashion. How many touchings of this the band is only deciding the 6 or 7 order, that you can easily see from the response of the Chebyshev filter itself. So this elliptical and circular, which pattern is this filter obeys? That's what the question is. And then given the correctly represents this. Yeah. When you write a Verilog code for FIR filter or IR filter, you are supposed to have the equation of this FIR filter and IR filter in the time domain. The discrete y of n equal to something x of n, some coefficients into the feed forward coefficients in case of into input, delayed inputs in case of FIR. And that equation, how do you represent it in the Verilog code? That's the question is about. So if the coefficients, you can use in Verilog only the shift operators, right, to represent the coefficients. So very accurate 1 by 8 is okay. I mean, you can shift it 3 times. So how do we use the shift operators to represent the coefficients in the Verilog? That's the question about here. And how do you introduce a delay in the Verilog code, x of n or x of n minus 1, x of n minus 2. So how do you introduce a delay? The non-blocking assignment comes into picture, and the non-blocking assignment continues one by one after the other. Okay, we'll introduce a flip-flop. Each delay is introduced with the flip-flop. So that is the question. How do you represent the equation in Verilog? For FIR as well as IIR, you have to practice, or you have to write a code for that. It's a very simple code. You can a few examples we have given in the lectures also. You can have a look at them. And this question is about if you just right shift it 2 times. This is arithmetic shift. So careful about the arithmetic shift and the normal shift. The arithmetic shift would do the sign extension. Okay, that it will take care of the sign extension as well. So if the negative number is there, if you are shifting, that the leftmost bits will be occupied with the sign extension. So I have explained that in one of the lectures. Please go through that and then answer these questions here, the transfer function, that also. And similarly, the transfer function, if the Verilog code is given, suppose an equation in the Verilog code is given, which transfer function it represents? The transfer function of the filter. This is obviously an IIR filter in which the coefficients are given as 43 by 32, 41 by 32, 31 by 32, and 5 by 32 in question number 13. But you need to see the y equal to x plus right shifting 1, right shifting again, and right shifting 2, right shift 5, and right shift 4. If you add up together, this is it representing which coefficient here? Okay, so that's the question about 13. And 14 is here, the difference equation again in Verilog. So what is the equation here? Okay, what is the y out? And you need to, from the test bench. So this code you have to do it. See, this question I want to tell you. 14. You write the code, and any simulator you use it, the Xilinx Vivado or any of the simulator which you are working on, and use this test bench and find out the output. Okay, and answer the question. You need to simulate it in the any simulator. Okay, and then answer the question at 65 nanoseconds. What is the output this impulse response gives you? Okay, that's the question about 14. And then 15, again, similarly, you have to run this code in the simulator, the code which is given. IR filter difference equation as well as the test bench is given. So with this test bench, run the code and get the impulse response, understand the code as well and the test bench also. Okay, and pick up the answer which is correct here. Impulse response at 95 nanoseconds. What is the response from the filter? 16 is also about the IF filter difference equation, and very different difference equation which are dealt in the lectures are used here. If you notice the filter equation, and get the step response here. So instead of impulse response, get a step response. The test bench is given for step response, making the reset for 1 for some time, and then reset becomes 0. And you see the input xn is 0 for some time, and then it made it 100 for rest of the time when reset is 0 in this case, like question number 16. Okay, question number 16 is step response. The previous two questions are based on the impulse response, and the 17 is also a step response for different equation. And yeah, that is the magnitude of a step is less. I mean, for 50 the step is only 50 u of n in that case, and previous one is 100 u of n. And what's the response at 155 nanoseconds? So you can observe it from the simulator waveform viewer, and then write the answer, pick the answer from this. Similarly, for FIR filter, we have used the various tab. The code which is already there in the lectures, that code is simply used, and obtain the impulse response for that filter. And what's the impulse response for FIR filter at this time? Test bench and everything. These questions, last 5 questions are basically getting the FIR filter and IIR filter impulse response and step response. And the step response also, if you have the 100 magnitude difference, like 100 or 10 or 50, what should be the response of it? So this is about the impulse response FIR filter. Then the coefficient similar at 500 nanoseconds. What's the output? So these are the questions in assignment 10. Assignment 10, right? 10, yeah. Assignment 10. So that is week 10. Is that 11 is, yeah. About 11, I quickly go through that. This is, see, 11th week. 11th week is now 11th week is about the DFT, FFT, and then STFT and its variants. Basically, the question is about that. STFT is considered to be this tuned filter, and what is the transfer function for it? Okay, so DFT and STFT thing, that difference you need to understand. So in DFT, all the bin indices can be obtained. K is varying from 0 to n minus 1. In STFT, you will have focus on only one bin which you are interested in. So from the input signal, which harmonic or which fundamental you wanted to extract from it. So instead of calculating all the bin values x of k, you can get only one bin index values from the input signal using this STFTs. And once you have the transfer function, what are the pole locations of it? That's about the second question. And the third question is about the again, the time domain equation, discrete equation of the STFT. And fourth is hopping DFT. Instead of sliding the window by one sample in the hopping DFT, you can choose this number of samples in the one hop. L equal to 4 or L equal to 5 or 6 or any of the number. That is about the hopping. And similarly, in hopping also, you would be interested in one bin index. And this is asking the transfer function of this hopping EFT. If the fifth question is about giving an x of t, a signal is given, and what signal rate it is sample. Okay, what is the frequency rate at which it is sample, and what is the DFT you are taking, and in the DFT equation you substitute it and they get you have to get the DFT of that signal. So what are the samples you get it when you sample it using the Nyquist criteria? This is 8 kilohertz is very well obeying the Nyquist-Shannon's theorem, because the maximum frequency here is 2K only, and get the samples as well as the DFT coefficients, what you get from that. This is the 5th question. And 6 is about, this is, if you have the DFT of the unshifted signal, and what should be the DFT of the shifted sequence. Okay, so when you have, you need not compute the whole DFT again for the shifted sequence. Use the shifting theorem and find it, find the output. So if x of k is known, and for x of n, and what is the x of n minus 2? So it should be e power j 2 pi k n by n, and the n is left shift or right shift, depends on that. You have to put the decimal. So find the x of k from DFT, that is x of 2, and then find the shifted one. That's the problem here in question 6. 7 is again about the DFT equation and the what is the shifting theorem is. So very simple. You have to pick which of them are correct here. And 8th question is again the samples are given. A few samples, 8 samples are given, and 8-point DIT algorithm using the FFT computed, and what should be in the butterfly structure, first second stage outputs. How do you compute first stage and second stage outputs or third stage output? In the 8-point there will be 3 stages. So this question is about put it in that diagram or equation and obtain the first and second third stage outputs. Also the case of 9 is DIF algorithm. So the DIT and DIF algorithm already you have I mean given in the lectures. Can refer to the lecture, and whether you would get the ordered output in the FFT, or you will have the bit reverse output. So DIF would give the bit reverse one, so you get you can pick the answers from this. So DIT and DIF algorithm needs to be referred. And the 10th one is DCT. Just use the MATLAB DCT command. And DCT even symmetrical, only one type of DCT I have discussed in the lecture. That is even symmetrical DCT, how to obtain, and that too from DFT. Okay, so obtaining DFT and then how to separate the coefficients from DCT, that would be interesting if you learn and do it actually for a given sample. Just take one problem, maybe this problem, and compute the DFT and then extract the DCT coefficient, the procedure which is defined in the lectures as well. Or you can use the simple this MATLAB command and get the coefficients. What are the coefficients you get from the DCT? Because you need to understand what is the basis function for DCT and DFT, and that is what the question is about. So these are the questions we were if you have any further questions, we are addressing through forums. And right now I would stop here, and I would request Shanti to take over.
Yeah, please. Yeah. Thank you, ma'am. Thank you for the introduction. And hello, everyone. I'm Shanti. I am working as a senior online course developer at MathWorks, makers of MATLAB and Simulink. So let me quickly share my screen and start the session. Yeah, so I hope I'm audible and my screen is visible.
Yeah.
Yes.
Yeah, thank you.
Yes.
So welcome to today's tutorial on signal denoising using FIR and IER filters in MATLAB. So in this session, We'll begin with an engineering problem related to signal denoising. We will discuss why denoising is required before any signal processing tasks or applications. Next, we'll see how to solve the engineering problem we have. As part of it, we'll start with MATLAB Online, available for this NPTEL course, FPGA based signal processing. Following that, we will do some hands-on activity focused on signal denoising using FIR and IAR filters. We'll end the tutorial by summarizing the key takeaways and a Q&A session. If you have any questions during the session, please post them in the chat and I'll try to address them then and there. Or we can also discuss the questions during the Q&A session. One thing which I would like to emphasize before I start the session is today's tutorial focuses on using MATLAB to denoise signals. I'll not be covering much about the theory on filter designing and different digital filters. So let's get started with the engineering problem we have. So in many engineering applications, signals contain important features as well as noise, both of which are distributed across a wide range of time and frequency scales. So for any applications, extracting these meaningful information from such signals requires the ability to distinguish between fine details, which is useful content of the signal, and the noise component. So here, consider a scenario where a vibration sensor is mounted on an industrial motor, which records the acceleration data at a sampling rate of 5 kilohertz. And talking about the signal which is getting recorded, the signal contains useful vibration information related to machine health, which is below 500 hertz, and a high frequency noise due to some electrical interferences, which is beyond 1 kilohertz. So the question here is, how can we design a digital filter that reduces this high frequency noise while preserving low frequency fault relevant vibration features? But this problem has a few practical complications that drive the filter design choices we can take. So in a vibration signal, so the noise need not be always just some random noise. It can be a narrow band high frequency interference, which requires meaningful selection of stop band attenuation. So identifying filter specification is very important when coming to filter designing. And another challenge here is fault-related components can include transient events, which are sensitive to phase distortion and group delay. So these challenges directly influence the choice between FIR filter and IAR filter. So talking about why denoising is important, denoising is usually the first step before any signal processing task, as you might already know, because most signal processing algorithms assume that the input signal represents the true physical phenomena. And the interference or presence of noise violates this assumption and can distort or completely mask the information you are trying to extract. So hence, denoising is usually the first step before any signal processing task. And addressing these challenges in the filter design or signal denoising requires careful selection of filter specification and filter types, as I mentioned before. So in this tutorial, we'll compare the results from IAR filter and FIR filter in solving this engineering problem. And the solution approach we have today is broadly divided into multiple minor steps. So first, we will start with loading the signal, and that means bringing the raw data or raw signal that needs to be analyzed. We will then inspect the vibration signal in both time and frequency domain. Next, we will derive the filter specification from the signal spectrum. And with the identified filter specification, we'll first design an FIR filter and then apply that FIR filter to the noisy vibration signal and validate the results. After this, we will design an IAR filter and apply it to the noisy vibration signal. And then finally, we'll compare the results from IAR filter and FIR filter and draw some conclusions. So as a first step to solve the engineering problem, we'll get started with MATLAB Online. All the registered learners to this NPTEL course, FPGA based signal processing, have access to MATLAB Online and have access to these set of products. I have a work live script for you to practice along with me. I'm sharing the MATLAB drive link in the chat, which includes two files, one work script and one solution script you will find. In this session, we will work with the work script, where you will find some placeholders to fill in and do the activities. The solution script you can refer after the session. So I request everyone to add the folder to your MATLAB drive, and I'll also post the instructions in the chat on how to add the files to your MATLAB drive. You may just click on this MATLAB drive link, which I posted in the chat, and click on add to my files to copy the folder to your MATLAB drive. Let me know if you face any difficulties in copying the files to your drive. I hope everyone have accessed the work script for this session today. And as I mentioned before, all the registered learners to this NPTEL course has access to MATLAB Online and the required toolboxes. You might have already accessed MATLAB Online through this NPTEL page. I'll just reiterate the steps once more. So you go to the FPGA based signal processing course page on NPTEL. And you can find an option on MATLAB. Okay, here I'm on the FPGA based signal processing course page. Here you can find on the left an option called MATLAB, where you can see two options, MATLAB Access and MATLAB Training. If you click on MATLAB Access, you will find instructions to get started with MATLAB Online for this course. So first step is to create a MathWorks account if you don't have already. And then you can click on the link on step 2 to access MATLAB for your NPTEL course. This will directly take you to the MATLAB online page. So once you open the work script, which I provided in the MATLAB Drive link, it will open up like a live script. I hope everyone could open MATLAB online and open work_filter_design.mlx file. And this will be our work script for today's tutorial. And for easy navigations to different sections, here there are table of contents that is linked to different section in the live script. You can click on a specific heading and it will navigate you to that section in the live script. So our engineering problem was is to how to design, how to denoise a signal using FIR and IIR filter. So as a first step, let's generate a representative signal here. So before designing a filter, we need a signal that reflects real world behavior, right? So since real measurement data may not be readily available, I have generated a synthetic signal here that mimics an industrial vibration measurement. And in real practice in industry, this step corresponds to loading the collected sensor data. So the code is already given for you. I'm not going to the details of signal generation as this is not our primary objective for the session. So talking about the signal which I have generated here on a high level, it is generated in a sampling frequency of 5000 Hertz. I have stored it in a variable called fs. And the generated signal has certain characteristics, which means the low frequency signals or low frequency vibrations are considered as useful vibration components. So I have kept the useful frequency as 120 Hertz and 320 Hertz, which is below 500 Hertz, which makes below 500 Hertz, whatever frequency components are there, we are considering it as
Sorry
useful
to
components.
disturb you. I think this code is not projected in the screen.
Oh, okay. One second.
Yeah.
I hope it's visible now.
Yes. Yeah.
Okay, thank you, ma'am. Yeah, so I was talking about signal generation. So as I mentioned, the code is already added for you. And talking about the signals that we have generated, I have considered 120 Hertz and 320 Hertz here as useful vibration components. And also I have added few noises, some high frequency noise, the range of 1800 Hertz. And I have generated a vibration signal, which is saved in a variable websig, which has both useful component and a noisy component. Let's run the section. So we have generated the noisy vibration signal. Now, before we design any filter, what is the first step? We need to derive the filter specifications from the signal. In real engineering work, filter cutoffs are not chosen arbitrarily. They come from these visualization or signal characteristics. That means we need to identify what part of the signal contains useful information and what part looks like interference or noise. So to make this visualization or exploration interactive, I'll be using here an app called Signal Analyzer app. So talking about the Signal Analyzer app very briefly, it allows us to quickly switch between different visualization. We can visualize a signal in time domain, frequency domain, or time frequency domain. And also we can zoom into specific region of interest and compare multiple signals even before filtering and after filtering without writing MATLAB codes. So let's visualize the vibration signal that we generated in time and frequency domain. For that, let's open the signal analyzer app. So to open the signal analyzer app, we'll go to the app section in the tool strip. We'll go to the app section in the tool strip. Click on the down arrow here and scroll down till signal processing and communication section. I'll repeat. We'll go to the app section, scroll down till signal processing and communication section, and locate the signal analyzer app. You can also launch the signal analyzer using the command. You can just type the signal analyzer in the live script or command window, which I'm highlighting here. Executing this line of code also will open the signal analyzer app. So I have opened the signal analyzer app now. We'll visualize the noisy vibration signal which we generated. So to visualize the signal, click on that signal WIBSIG where we have saved the noisy vibration signal. Now drag the signal from the workspace browser to the axis. Drag the signal from this workspace browser to the axis, and this will give you the time domain visualization of the vibration signal which we created. So note that the x-axis is in samples raw, right? So adding the time information to any signal before doing any analysis onto it is very important. So we need correct time information so that the app can place samples on the right time axis. This will help you in making the frequency axis in hertz and any time-based comparisons later. Like if you want to do or tasks like event timing or delays alignment. So adding correct time information is very important for any signal analysis. So for that, we'll go to the Analyzer tab in the Signal Analyzer and click on Time Values. We'll go to the Analyzer tab and click on Time Values. This will open up a small dialog box. Here, we'll select the second option from the drop-down, that is sample rate and start time. So we already know the sample rate for this generated signal, right? So the sample rate was 5000 Hertz. So we'll enter 5000 Hertz here. And let the start time be the default one, which is 0 seconds, and click OK. Now we can see the difference in the visualization. Now the x-axis has now become in time. Earlier it was in samples. Now the time axis is now in the unit seconds. And if you talk about this time domain visualization of the signals, you can see a collection of low frequency and high frequency component in this signal. But the question is, it's hard to justify the filter cutoffs just by analyzing the waveform in this time domain, right? You can't actually get the frequency information from this time domain visualization. So for that, we need to visualize the spectrum of the signal. So here, the spectrum helps us separate what we want to keep from what we want to remove. So in the Signal Analyzer app itself, we'll go to the display, the next tab next to the analyzer, and click on spectrum. In the display tab, click on spectrum. So now you see the frequencies or power spectrum or frequency domain visualization of the vibration signal. Now it's very clear that what are those frequency points which is useful in for this vibration signal, and which is that peak which is noise. So here, if you talk about the spectrum shows dominant energy, let's say below 500 hertz. And you can see an unwanted component which appears beyond 1 kilohertz, nearly around 1.8 kilohertz. So our goal is to remove or reduce the attenuation for this 1.8 kilohertz noise component. So this naturally leads to a design of or a decision making fact that we need to design a low pass filter. And what will be the pass band frequency, or pass band frequency can be like around 500 hertz, because below 500 hertz is what we have the useful vibration component. And the stop band frequency can be 1 kilohertz. So at this stage, we are connecting our observation to the design specifications. You are choosing 500 hertz because the spectrum indicates the useful content is concentrated here. And also you are leaving a transition band of 500 to 1000 hertz, because narrower transition usually mean higher order. So now at this stage, we have identified the filter specification. So next we will design the filter that can remove this 1.8 kilohertz high frequency noise. So for that, for now, we'll just minimize the signal analyzer app. And we'll go to the next step of filter designing. So first, we'll start with FIR filter. And for designing FIR filter, we will use a filter designer app or FDA tool. So basically in vibration signals, we normally care about the timing and shape of those transient impacts of the vibration components. So usually the first choice when it comes to filter design is a linear phase FIR design. And it's always, we usually start with a linear phase FIR design, mainly because of this reason that timing and the waveform shape will be preserved. So today we'll be using the filter designer app for designing the filter. Talking about a bit about filter designer app. Filter designer is a powerful user interface for designing and analyzing filters. You might have already used this in your course lectures. You might have already seen this FDA tool or filter designer app. And filter designer enables you to quickly design digital FIR or IIR filter by specifying the filter performance or specifications. And filter designer also provides tools for analyzing filters such as magnitude and phase response plots, and many more like pole zero plots and group delay. So let's launch the filter designer app. So as I mentioned for the signal analyzer app, how to launch it. Either you can launch through the app section, or you can run this filter designer command in the command window or the live script or in the editor window. So for now, we'll go to the app section and scroll down till signal processing and communication and locate for filter designer. So the filter designer window is open. Just talking about the interface here. Mainly, there are like three main section or three main regions in the filter designer. The first region, which I'm highlighting here, which I'm hovering my mouse pointer over, the current filter information region. So this region mainly gives or display the information on filter specification and responses for the current filter we have designed. And this region display properties like filter properties like filter order or like filter structure. Is it whether the filter is stable or not? So all the filter information is being displayed here on the upper half of the interface. On the upper right half, you will see the filter specification region or filter display region, we call it as. And here it displays various filter responses, where it mainly goes to the filter analysis part, where you can visualize the magnitude response, phase response, group delay, and filter coefficients, and pole zero plot. And in the design panel on the lower side, you can, this is where actually the filter design happens, where you can give all the filter specification which we identified in the previous step. And once all the specifications are set, you can click on the design filter, and this responses you will be able to see on the upper side of the filter designer app. So this is about the filter designer interface. Now coming back to the problem or the solution we are solving. So in step 2, we have identified the filter specification, and now we are going to design an FIR low pass filter. So in the response type, we'll select low pass. This is a default option or response type. And under the design method, we'll choose FIR filter. We'll keep the design method as equiripple for now. And in the filter order section, we'll keep it as minimum order. Let's not change all these default settings for now. And what we are going to change is the filter specification. Fs is the sampling frequency. So what was the sampling frequency for our problem? We have defined it as 5000 Hertz, right? So we will enter Fs equal to 5000. And we have also identified the pass band frequency and stop band frequency. So F pass here is a pass band frequency. So a pass band frequency, as you might already know, the frequency till where you want to let the signals go, right? Which what all frequency you need to preserve. So we'll define it as 500, because below 500 is where we have our useful vibration component, right? And the stop band frequency, we'll call it, we will give it as 1000 Hertz, because beyond 1000 Hertz is where our high frequency noise is present, which was nearly near to 1.8 kilohertz. So we will mention the stop band frequency as 1000. And here we have the magnitude specification in dB. The first one is pass band ripple, which will keep it as 1 dB as a default one. And stop band attenuation, we'll keep it as 60. Now the filter specifications are all set. Now we'll click on design filter. So once you click on the design filter, immediately on the upper panel, you will see the magnitude response of your design filter. So let's just observe the magnitude response and see what are those filter characteristics or responses that justifies our design. Now, if you look at the magnitude response plot, the response near 0 dB through the passband, that is like up to 0.5 kilohertz, which is our passband frequency, 500 hertz, it is set to 0 dB. So that means all the signals till 500 hertz is being passed through the filter. And after 0.5 till 1 kilohertz, which is our stop band frequency, the response drops strongly by the stop band frequency. And past that 1 kilohertz, which is our stop band frequency, the attenuation approaches whatever we wanted, like minus 60 dB. Stop band attenuation we defined was 60 dB, so it is exactly reflecting the same. So through this magnitude response, we can confirm that whether the filter that we designed can suppress high frequency noise while preserving the low frequency band of interest. So the magnitude response we just now we got actually reflects what was our design requirement. We need all the signals to be passed below 500 hertz, and above 1 kilohertz it should attenuate the signal, which will actually suppress the high frequency noise in our vibration signal. We'll also analyze the phase response. So on top of the filter designer, above the magnitude response, you can find so many options here. So this is magnitude response. Next to it, you can find the phase response button. So if you click on this phase response button, you will get the phase plot of the signal of the filter we designed. So here, as expected, we know that FIR is a linear phase design filter, right? So FIR linear phase designs typically show a phase trend that look close to a linear line. And this indicates that it preserves the waveform shape and timing even after filtering, which is very important in mainly in almost all vibration fault monitoring applications. And if you look at the group delay option, very next to phase response, if you want to collectively jointly see the phase and magnitude response, you can click here, the next button. And next is the group delay. So the group delay tends to be relatively flat, nearly constant. So mainly in vibration fault monitoring, impacts and transients are time localized features. So a more uniform delay helps preserve the event shape and timing. And this is especially important if the later steps and always the filter design also depends on what is the next step after denoising. So if the later steps include peak detection or envelope analysis or aligning evenly, this shape and timing preservation is very important. That is where FIR filter selection makes important. And make a note of the filter order here on the left side under the current filter information. So the order of this filter is 19. We'll see later how this differs for the same specification for an IIR filter. So now once we are happy with our design of filter, we can export this filter so that we can use it later, and we can see the what is the denoised signal with the application of this filter which we designed. So for exporting the filter, go to the files section, click on file and click on export. I'll repeat, to export this filter that we designed now, go to the files section. In the drop down, click on export. This will give you a small dialog box, as in where you have to where you need to export. For now, we will export to our MATLAB workspace, and we will export it as coefficients. Other options are you can export it as objects or system objects. For now, we will use filter. We will export it as filter coefficients, and we'll keep the numerator or variable names as default, and click on export. So it displays a message saying variables has been exported to the workspace. Let's minimize the filter designer for now. And let's move to the next step after filter designing, where we will apply this FIR filter to the noisy vibration signal. So for that, we will use a function called filter function to process this vibration signal. I'll post the code as well in the chat so that it's easy to follow. So here we are applying this designed FIR filter using the function filter and the filter coefficients which we exported from the filter designer app. So the filter function has 3 inputs here. The first input is num, which is our filter coefficients, which is the numerator. As we are dealing with the FIR filter, the denominator coefficients will be 1. And the third input is the noisy vibration signal. We are saving this filtered signal to a variable called sig filtered FIR. After we have the code in place, let's run the section. We have run the section. Now let's validate the results using the visualization. We will visualize the signal, filtered signal in both time domain and frequency domain. For that, let's open the signal analyzer app again. Let's drag the filtered signal using FIR filter to the axis, just like we visualized the noisy signal before. Let's also add the time information. For that, click on the analyzer tab, go to the time values and enter the sample rate, which is 5,000 here. This is same steps we did for visualizing the noisy vibration signal. So this is the time domain visualization for the filtered FIR signal. Let's compare it with the noisy signal and see how much the noise has been reduced. For that, click on the small box, small check box next to the vibration signal, the noisy one, so that both the signals are being displayed together now, and it's easy for us to compare. So the blue one is the noisy vibration signal, and the orange one here is the filtered signal using FIR filter. So here in the time domain visualization, you can see like this shape is being preserved, no change in the shape of the filtered signal, but few components are being removed, which means some noise has been removed here. But we can't obviously see which frequency component has been removed, right? So we'll go to the spectrum. We visualize the signal in the frequency domain for better interpretation. So here you can clearly see that below 500 Hertz, all the useful vibration signal is being preserved. and above 1 kilohertz, which was our stop band attenuation or stop band frequency, the signal is being attenuated largely. So that means it has suppressed the noise. So we can conclude that through FIR filter application, the noise at the high frequency noise has been significantly attenuated, but not completely removed. As you can see, the peak over here, a small peak, 1.8 kilohertz peak is still present, but it is been highly attenuated. So overall, we can say that the filtered signal is less noisy and the vibration features are preserved now. And the FIR filter is working as intended for our engineering problem today. Now we will see how an IIR filter works and what will be the output, filtered output, if we apply a IIR filter with same filter specifications. So for that, let's go back to the filter designer app. And now we will design an IIR low pass filter. So here we will see what is that difference between FIR and IIR filter. And normally by theoretical, you know that IIR filter achieve sharper transitions with much lower order, right? So mostly on with real-time applications, IIR filter is preferred. So now we will see it implemented, and we'll compare the results which we obtained from FIR filter, and which we will see what is the result from an IIR filter. Now, in the filter designer app, the filter specifications are same. The response type is low pass, but the design method, now we are going to use an IIR filter. Let's keep the design method as Butterworth. And all the filter specifications like the sampling frequency, which was 5000 Hertz, or passband frequency, stop band frequency, stop band attenuation, passband ripple, everything remains the same. Now, with this specification, let's design the filter. Click on design filter. Now we can see the magnitude response plot is being displayed here. So here in the passband, that is up to 0.5 kilohertz, the response stays close to 0 dB as expected, which means that the filter preserves low frequency vibration band, which we identified as useful. And between 0.5 to 1 kilohertz, which is our transition band, the response transitions downward. So this is normal because you intentionally left, because we intentionally left a gap between the passband and stop band, right? So there's a drop here, and beyond the stop band, which is greater than 1 kilohertz, the magnitude continues dropping well below minus 60 dB. So what does this drop means? Like the peak drop as compared to the FIR filter. So this means that the filter strongly suppresses the high frequency noises, which is exactly the requirement behind our design, right? So seeing the magnitude response, we can confirm that the IIR filter should reduce the high frequency electrical noise, which is beyond 1 kilohertz, and will retain the low frequency vibration content, which is below 500 hertz. And if you see the filter order on the left side under current filter information, with the same filter specification like FIR, the filter order here is very low, right? So earlier, if you remember, the filter order for the same specification FIR filter was 19, right? 19. So here the order is being reduced to 10. So this is the classic advantage of an IIR filter design, that FIR filter design, usually with the same specifications, it will have a higher order, but IIR filter will have a lower order. So we can say that overall, the IIR achieves the required attenuation with a compact design. That means a lower order, which basically translates to the fewer computations per sample and better suitable for real-time workflows. Now, if you analyze the phase response of the IIR filter, the phase starts near to 0 radians, and it increases negatively as frequency increases, reaching roughly around minus 15 radians here, right, by about 2 to 2.5 kilohertz. And obviously the curve is not a straight line. It bends noticeably with a steeper change in the phase at lower frequencies and a more gradual change at the higher frequency. So by theoretical, we know that this curved phase, the curved phase characteristics is typical of an IIR Butterworth design, and is a visual indicator that the filter does not have a linear phase. So in vibration signals containing transient fault events, this nonlinear phase can slightly alter the shape of impacts. However, the IIR design typically achieves the required attenuation, as I mentioned, with a lower order, so making it efficient for real-time workflows. Now we'll export this filter designed filter using the same way as we exported the FIR filter. We'll go to the file option, click on export, and here also we'll export as coefficients. Here it will be second order sections, and there will be scale values for an IIR filter. We'll keep the variable names as default, the second order section metrics as SOS, and scale values as G. Let's click on export. Variables has been exported to the workspace. Now we'll apply this designed IIR filter to our noisy vibration signal. So remember, earlier we used a function called filter function for applying the FIR filter. So filter function is mainly for causal filtering, means it is suitable for a linear phase filtering. But since IIR filter and some FIR filters do not have linear phase, we can use a little more advanced filtering function, which is basically called anti-causal zero phase filtering. You can read about this zero phase filtering here. I have given a link over here in this live script. You can read about it later after the session. So here we will be using a special filter function called filtfilt, which is basically a zero phase filtering, which is suitable for a non-linear phase type of filter. So we'll apply this designed IIR filter to our noisy vibration signal. Let's run this section as well. We have now applied the IIR filter. Now let's validate the results in the Signal Analyzer app. Let's go back to the Signal Analyzer app. We'll uncheck whatever was displayed earlier, the FIR filtered signal and the noisy vibration signal. Let's first visualize the filtered IIR signal. click and drag to the axis. Set the time information. Sample rate is 5,000.
This filter is like this. It's not filtering anything.
Now, if we compare the noisy vibration signal where we started and the filtered IAR signal, we can see there is some reduction in few components. And as I mentioned before, to see the frequencies specification, let's visualize the spectrum. So when you see the frequency domain visualization of this IAR filter, it's clearly seen that below 500, all the useful vibration signals are preserved, and above this cutoff, like above the stop band frequency, there is a huge reduction in the noise. The noise peak is also getting reduced here. So we can say that the filtered signal is less noisy and the vibration features are preserved. So we can say the IAR filter is working as intended for the engineering problem we have. Now, if we, as a last step, we can compare the FIR and IAR results. So for that, let's visualize the filtered FIR signal here itself in the signal analyzer app. So as clearly seen, till now what we have done, we have designed FIR filter, IAR filter. We have applied both the FIR low pass filter and IAR low pass filter to the same vibration signal with same frequency or same filter specification. And we can say that both filter reduce high frequency noise, but they achieve this using different internal structure and some trade-offs. So if you see the visualization in the signal analyzer app on this FIR and IAR filtered signal, both FIR and IAR meet the magnitude response, and IAR typically achieves this with much lower filter order. And we can also see that the attenuation, the amount of attenuation is lower in IAR filter. The noise peak also is getting removed in the application of IAR filter. So this doesn't mean that FIR filter didn't met our requirements or expectations. But the choice of filter, FIR and IAR filter, is highly dependent on the applications, what follows next after signal denoising. So both has its own advantages and disadvantages. So depending on the application or the design requirements, we can select between FIR and IAR filter. So to summarize what we did today, we designed a digital filter that reduces high frequency noise while preserving low frequency component, and we compare the FIR and IAR filters. So we can say that what are the key takeaways from this exercise? Both FIR and IAR effectively remove high frequency noise from the noisy vibration signal, and FIR filters are preferred when waveform shape and timing are important, and if the computation complexity and the lower order makes sense, you can go for IAR filter. And IAR filter is very much suitable for real-time and resource-constrained applications. So we can conclude that the choice between FIR and IAR depends on whether the priority is phase fidelity or computational efficiency. I have given additional resources also in the live script. You can refer to those additional resources. The additional resources includes details, a few more examples on designing different types of filters. And for example, this arbitrary magnitude filter design, which is a very special type of filter. Some examples are given. You can see here using the link here. And also there are links on getting started with MATLAB to HDL workflow, which is very specifically to the filter design. How we can generate code using HDL coder and FPGA synthesis from MATLAB. So these last two resources will help you in modeling the filter design using HDL coder. Yeah, thank you. Any questions anyone have?
Yes, good afternoon, ma'am.
Yeah.
मैम एक तो हमारा सिग्नल्स होता है फाइनाइट इंपल्स रेस्पॉन्स और एक इनफाइनाइट इंपल्स रेस्पॉन्स. मैम फाइनाइट इंपल्स रेस्पॉन्स का जो सिग्नल्स होता है वो मतलब उसका एंड कहाँ पे है सिग्नल का? ये वो कुछ टाइम के बाद जीरो हो जाता है या फिर मतलब एक फिक्स वैल्यू होती है उसकी? और इनफाइनाइट में मैम वो इनफाइनाइट तक जाएगा सिग्नल? मतलब थोड़ा सा अंडरस्टैंडिंग चाहिए था इन दोनों के बारे में ना.
So in terms of FIR, if you talk about the FIR signal, the finite impulse response signal and IAR signals, so always if you see the equation of FIR filter or IAR signal filter, so you will see a boundary limit for FIR, like summation of 0 to a constant value. So that is, we have a definite length for FIR signals, but IAR signals is as name implies, it is spanning to minus infinity to infinity. But when it comes to MATLAB implementation, it is not practical to have a finite thing. So it will have a definite limit for IAR filter as well, or IAR signals as well. But we can't say that exactly what is that number for infinite signals.
Ma'am, how to decide cutoff frequency of vibration sensors of any other sensors? How to decide?
Yeah, good question it is. So in today's example, we had generated the signal, right? So yes, we had defined, okay, till this cutoff frequency is or till this frequency is what we have the useful information, and beyond this frequency is what the noise is, because we have generated that signal. But in practical cases, we will define or we will decide on the cutoff frequency purely on the visualization. So we will acquire those signals from different sensors. We will visualize the signal in time domain and mainly in the frequency domain, so that we can see what is that frequency where you can see the noise coming up. So usually the noise will be random, right? It won't be like a narrow band or like a peak signal. So by visualizing or by analyzing that frequency spectrum, we decide on the cutoff frequency of the signal. And there are like other advanced techniques also, like visualize the signal in time frequency domain and see the energy distribution and event detection. Things, different advanced algorithms are also there in real life applications.
Decided by the by data from the data sheet ना, ये maximum vibrations सिग्नल मतलब जो सेंसर्स है वो कितना मैक्सिमम वाइब्रेशन अचीव कर सकता है. अकॉर्डिंग टू दैट वी विल डिसाइड द कट ऑफ फ्रीक्वेंसी.
Yeah, that is also one method, but that actually
because we get from the we are designing TPMS, tire pressure monitoring system. We are using pressure sensor. So pressure sensor is inside the tire. So we don't know कि कितना वाइब्रेशन उसके अंदर आएगा टायर का जब गाड़ी रफली चलेगी. तो उस वाइब्रेशन को हम मतलब कैसे उस वाइब्रेशन को डिसाइड करेंगे कितना वाइब्रेशन आए. तो माय क्वेश्चन इज दैट कि प्रेशर सेंसर का जो प्रेशर होगा वो तो मैक्सिमम होगा ही, और वो वाइब्रेशंस को कैसे हम डिसाइड करेंगे मैम? कितना वाइब्रेशंस, फ्रीक्वेंसी कितना वाइब्रेशन आएगा, उससे कितना नॉइज जनरेट होगा? दैट आई एम टॉकिंग अबाउट द एक्सटेंसिव नॉइज। एक्चुअली एक्सटर्नल नॉइज हो गया वाइब्रेशन नॉइज आपका, तो उस वाइब्रेशंस को मैं कैसे डिटेक्ट करूंगी? कितना वाइब्रेशंस आएगा इसमें टायर के अंदर? गाड़ी कितनी स्पीड पे चल रही है, 120 किलोमीटर पर आवर की स्पीड पे, या फिर कितनी स्पीड पे? तो मैम ये थोड़ा सा मेरे को पूछना था।
Okay, so you mentioned that you have a data sheet on what are those limits for the sensors, right? So when you get the signal, like from the pressure sensor, whatever it is, when you get the signal, you will be able to see the variations in the energy spectrum, like energy spread across the signal. So if you find that is beyond that particular limit, that is clearly a noise.
Okay.
It won't be like a useful information what we have. So that's what I mentioned earlier. In normal or like in simple, like if there are like very less noise interference or like 1 or 2 frequency change in the signal, you can go for the frequency spectrum of the signal. We can initialize the frequency spectrum and decide on the frequencies which is noisy. But if the noise is spread across the entire range of the signal, like a broadband noise, then in that case, what you can do is you can go to the frequency time domain representation, time frequency representation, where you have the techniques like spectrogram and scaleogram, where you will be able to see the difference in energy distribution for each band. Okay. So in that way, you can actually see which is that band having like high energy, which can be categorized as noisy, and which is that useful information.
Okay, ma'am, because I face some problems in some projects because I'm working in CSIR Chandigarh. I'm working on Sukhoi 30 aircraft. So some vibrations noise and some external white noise, impulse noise are coming from the external environment. So that is, I think, more beneficial for me.
Okay. Basically, when you talk about white noise is kind of a broadband noise. It will be spreaded across, the wide range of signals. To remove white noise, basically, I'll talk about denoising if the noise type is white noise. Yeah. So in that case, simple low pass filter or high pass filter won't work. You can better go with some median filtering or average filtering because it will span across the entire range of signals. It won't be like a special cutoff frequency.
Okay, ma'am.
So if the end goal is to remove the white noise, don't go for low pass or high pass filter. Better go for sliding window or moving average filters.
Yes,
I can give you some links.
Curve fitting method also, na?
Yeah, right. Then you should basically go with the windowing method of filtering.
Okay, ma'am. Thank you so much.
Yeah, thank you.
HDL, no?
तो मेरा क्वेश्चन ये था, आपको कोई भी अगर इसको फिल्टर करना है, सर मेरा क्वेश्चन ये था, ये एक्चुअली दो फिल्टर के बारे में मतलब बता रहे थे.
I muted.
If you don't have any other questions, we can wind up the session. You can find all the resources in the drive link I shared.
Ma'am, good afternoon. I'm working as in a college. I wasn't able to attend the session because of classes, academic activities. Is there any recorded thing available for this session, ma'am? Is it available?
Yes. Yeah. Yeah, it will be posted in YouTube. This live session you can watch later.
Right, ma'am. Thank you. Thank you so much.
And there is a question from you also to just demonstrate the HDL coder, if I recall correctly.
Yes, ma'am.
So that there is a material provided by Shanti. In the live session, she had given the link also. You can go to that link and explore it.
Okay, ma'am. Thank you so much, ma'am.
Yeah.
Thank you.
Okay. Yeah, I think. Shall we wind up, Shanti?
Yeah, ma'am. Thank you. I know. Yeah.
Thank you so much for
Thanks, ma'am.
joining, and thank you, Shanti, for giving this insightful session. And hope they were enjoyed this session. And it will be posted. The recording is available in the YouTube, and you can watch over it later. And the design you can practice, and MATLAB link and the materials resources related to it also is shared in the course page. You can utilize this opportunity to explore further. Thank you so much for joining. Thank you. Thank you.
Yeah. Thank you, ma'am. Thank you all.
Thank you.